All right, so this is a classic limiting reactant problem. You know, yield from one reactant, yield from the other reactant, pick the smaller one. That's a limiting reactant. This is the theoretical yield, and then calculate how much excess reactant remains unused. So this is a classic limiting reactant problem right there. The equation for one method of preparing iodine is, okay, so this is sodium iodate plus sodium hydrogen sulfite. So this one looks like a metathesis reaction. You know, initially when you look at it, it's metathesis, and there could be also a metathesis reaction, but it's going to be sodium with bisulfite and sodium with iodate. So there's no metathesis happening here. Just because there's no metathesis doesn't mean there's no reaction, because so we got to look for acid base and redox. And so I can tell a redox is going to happen here because iodate's an oxidizer, and bisulfite, sulfites are reducers. You know, when you buy wine, you know, when you buy wine, there's a little label on the wine. I stopped drinking wine, but I used to drink wine. Not because of the vinegar that I got the other day. I mean, that was not the other day, but that was years ago. But wine says it contains sulfites. And so I was saying, oh, that's interesting. What do? They, you know, when they put sodium sulfite in it, this is sodium sulfite, or this is sodium hydrogen sulfite. Sodium sulfite would be Na2SO3. No. So I looked into it. They don't put sulfites in there. Do you know what they put in? Into wine? They put sulfur dioxide. But, you know, I wonder, why do they call it sulfites when they're putting sulfur dioxide? Maybe sulfur dioxide, you know, people look up sulfur dioxide and they go, wow, you know, I don't want to, you know, sulfite might sound more innocuous than sulfur dioxide, which is a gas. But if we take a look at what sulfur dioxide, let's take a look at sulfur dioxide. Sulfur dioxide. It's released in volcanic activity, totally. Sulfur dioxide. This is the sulfur smell that people get. Matches, burnt matches, that kind of stuff. This kills people, basically. Air pollutant safety. Safety, inhalation. Mildly toxic. But maybe sulfite sounds better. But when you look at sulfur dioxide and sulfite, redox-wise, they should be very similar, regardless. And so let's take a look at sulfite, SO3 2-, and then sulfur dioxide. And when I look at these are very similar redox-wise because, you know, over here, oxygen is -2, that makes sulfur +4. Over here, oxygen is -2, so -2 times 6 is -6. This has got to be +4. +4 minus 6 gives us -2. And so you can see redox-wise, they're going to be very similar because this is sulfur +4, this is sulfur +4. So look at wine. You know, we could look at sulfites, SO2 in wine. You know, it says contains sulfites. And what they're using is sulfur dioxide. The antioxidant effect of sulfur dioxide prevents the natural aromas of the grapes and wine to get oxidized. Should some oxygen come in contact. And so the wine I bought in Joshua Tree, actually Yucca Valley, didn't have enough sulfites because the sulfites were the limiting reagent. If there was plenty of sulfites in there, then the oxygen that leaked in there could attack the sulfites or sulfur dioxide and oxidize that, you know. But what happened was pretty soon, you know, you want the antioxidant to be the excess reagent. But pretty soon there was just too much oxygen. So it must have been leaking for a long time. And the amount of SO2 went down, down, down until it was all gone. And then once it's all gone, well, then your limiting reagent, which is the sulfites, the antioxidants, what's supposed to be protecting the wine, is no longer protecting the wine. And then the oxygen is going to want to attack. It'll want to attack other things like the ethanol. Ethanol is easy to oxidize, and some of the fruity flavors of wine are easy to oxidize. And so to make fruity wine that smells of something like grapes, it was made from whatever. SO2 helps a lot. So. But there's, of course, there's debate, because who wants sulfur dioxide in wine, etc. Okay, so when I look at this, I see redox, happening here. That's why that got in here. And so, yeah, they're definitely a redox. Iodate's an oxidizer. Sulfites are reducers, And so there's some redox going on. So iodate takes electrons, eventually forms iodine. Iodine here is +5, goes to 0. Sulfur is +4, goes to sulfate, which is +6. This is bisulfate. So there's some redox happening there. This one's more skeletal, you just mix it together and see what happens, Iodate is not on the chart, nor is sulfite or bisulfite. Sulfite and bisulfite are going to have the same redox, they're both +4, which is the same as SO2, And so we have 6 kilograms of sodium iodate, 7.33 kilograms of sodium hydrogen sulfide. So we calculate the yield from this reactant, and see which one's smaller. So calculate the yield from this reactant, we get 3.85 grams or kilograms of iodine. Calculate the yield from this reactant and see which one's smaller. Well, 3.58 is smaller than 3.85. And so which one's smaller is our theoretical yield. And so this is our this is impossible. We can't form that much. And so this is our theoretical yield here. And therefore, this is the limiting reagent here. This is the excess reagent here. We have too much of this and not enough to react. And so our excess reagent was the oxidizer. Our limiting reagent was the reducer here. So how much oxidizer are we going to have unreacted? And so the reducer was the limiting reagent, okay? So in order to do that, we start off with initial, this is how much we started off with, 6 kilograms, minus the amount used. This is the amount used by the LR, The amount used by the LR, we figure out how much that is stoichiometrically. So we drop the LR here. In this calculation, we find out how many kilograms of excess reagent were used, sodium iodate here. And so we go from kilograms eventually to kilograms of sodium iodate. And so this is how much sodium iodate was required to react with all of our limiting reagent here, 5.58 kilograms. And so we'll plug that in here, subtract the 2, and we have about 0.5 kilogram unused left over. So again, this is the classic stoichiometry. This kind of pattern here, or this kind of calculation, you should know well, because that's a standard calculation. And so you can practice those. All right. A mixture or tester of phosphorus trisulfide and powdered glass is in the white tip of strike anywhere matches. Okay, so tetraphosphorus trisulfide must be unstable, maybe. And so that decomposes into flammably, in the flame, redox. P4S3 is made by the direct combination of phosphorus and sulfur, this reaction. So again, we're given the amount of phosphorus, this reagent, and the amount of sulfur, 126 grams of this reagent. And so we calculate the yield from this, and see which one's smaller. That's a theoretical yield. That's how many grams of the compound can be formed theoretically. How much will be left over? Okay. Well, the limiting reagent, nothing's left over with the limiting reagent. And so here, we calculate yield from phosphorus. It gives 236 grams of P4S3. Calculate the yield from sulfur, which gives 288. And then see which one's smaller. Well, 236 is smaller. And so this can be a theoretical yield. Yeah. This yield is impossible because we'll run out of phosphorus. This will be our limiting reagent here. We're going to have leftover sulfur. We're going to have no leftover. So how many grams of sulfur are left over? We'll calculate. How many grams of phosphorus are left over? 0. Limiting reagent is completely used. So 0 grams of phosphorus left over. This is white phosphorus, by the way. White phosphorus is not so stable. The yield is the smaller amount, 236 grams, and then we calculate how much is left over. So we started off with 126. That's our initial. And this is the amount used by the limiting reagent. The amount used by limiting reagent we get by calculation. That is 133 grams of limiting reagent requires 103 grams of sulfur. So we used up 103 grams here, and that leaves us with 23 grams left over. Okay, these are energy conversions. And so kilojoules to kilocalories. So I go kilocalories to calories and calories to joules, 4.184 joules per calorie. They do it in one step, you know. I do it in 2 steps. What number of calories is the same as 651 joules? So this is just this conversion, you know, 1 calorie is 4.184 joules. So dimensional analysis conversion. Determine the number of kilocalories equivalent to that. So I would go joules to calories, calories to kilocalories, joules to calories, calories to kilocalories. So they did it the way I do it here. I wouldn't have rounded here. I would have shown the step before rounding it and then rounded at the end. So these are more conversion practices. When 15 grams of carbon is burned, 493 kilojoules of energy is released. Calculate the number of calories or kilocalories. So just kilojoules to joules, joules to calories, calories to kilocalories. So kilojoules to, oh, they do it in one step. I do it in multiple. Each day, 5.8 times 10. So 580 kilocalories of heat is transferred out of the body by evaporation. How many kilojoules per year? Wow, okay. Per year. So, you know, there are 2 ways. We could do this as a ratio, or we do this like this. I would do this like this, you know. I'm given 1 year. 1 year. And then where am I going to go? Well, I could go to days, let's say, because they're talking about days each day here. So we'll just say 365 days per year. And then I have this one that gets rid of days. That is each day 5.8 times 10 squared. So each day 5.8 times 10 squared kilocalories. And so this is a conversion factor that works just for this problem right here. And so it goes from days to kilocalories. And then we'll go to calories, you know, 1,000 calories per kilocalorie. And then from calories, we could go to joules, 4.184 joules per calorie. And then from joules, we could go to kilojoules. 1 kilojoule is equivalent to 1,000 joules. And so that should give me, for 1 year, how many kilojoules heat that is. This is the way I would have done it. They did it by ratio here. This is fine too. They have kilocalories per day, and then they convert the top into kilojoules, and then they convert the bottom to years. And so you could leave it like this. This is another dimensional analysis type problem where we get it this many kilojoules per year. I did a little bit differently, you know, where I didn't start with a ratio. I just started with a given 1 year. Either way is fine, this particular problem. Stoichiometry is important, so that's why I'm going through all these problems. Energy is transferred from sunlight in the photosynthesis reaction. Okay, so we saw the photosynthesis reaction earlier. The amount of energy is 2.82 times 10 to the third kilojoules per mole of sugar formed. Okay. What are you supposed to do? All right, I think they want us to write the equations for this. Now, when we balance this equation, let's see yeah, all right. There are two ways of doing this. This is 2.82 times 10 to the third kilojoules per mole of sugar formed. And so when we look at this equation, the balanced chemical equation is 6 CO2s plus 6 waters yields 1 mole, 1 sugar here. And so we have this much energy is required for this. And so this is where we're using energy as a reactant. It's an endothermic reaction. And over here, this is a standard way of writing it. If it's endothermic, we give it a positive sign. If it's exothermic, we get a negative sign. And so we'd write the delta H. Now this little subscript here, R, means reaction. So this is delta H for the reaction as written here. And that's plus 2.82 times 10 to the third kilojoules. Now, if we wanted to form 2 moles of sugar, we'd need twice as much energy. 3 moles of sugar, we'd need 3 times as much energy. This one's fixed though. When we write it like this is not, there's 2 ways of doing it. If we have the reaction written here, that's fine. We could leave it like this, kilojoules. If this is separate, sometimes we'll write kilojoules per mole, you know, like they did up here. Kilojoules per mole of sugar. And so that's an alternate way, but we don't have to write it because the reaction's written here. And so it's per 1 mole of sugar, or per 6 moles of CO2, or per 6 moles of H2O, or per 6 moles of O2. We already went through this earlier. And so oftentimes we'll just write it 2.82 times 10 to the third kilojoules per mole of sugar, or per 6 moles of CO2, per 6 moles of water, etc. The electrolysis of water is an endothermic reaction. So this is the same deal. We can either add this as a reactant, but we have to look, it's 286 kilojoules per mole of liquid water. And so it depends on how we write the reaction. Normally when we write the reaction, electrolysis of water, it's going to look like this. H2O liquid goes to H2 gas plus O2 gas. Now to balance this, we typically write 2 waters here and we get 2 hydrogens here. But this is 286 kilojoules per each mole of water. This is 2 moles of water. And so what we'd have to do is we'd have to double this for 2 moles of water. So this would be, or we'd have to cut this in half. If we cut this in half, then we get H2O liquid goes to H2 gas plus 1/2 mole of oxygen, which is fine. And in this case, it would be 286 kilojoules plus this. That would be an endothermic, or we write it off to the side. In this case here, there are 2 ways of writing this. In this case, it'd be delta H, like this, is equal to 286 kilojoules per mole of water per mole of H2O, but we have 2 moles of H2O as written. And so this would be delta H is equal to double 286 would be 572. So we'd have 572 kilojoules. So if we wrote it like this, delta H equals 570 kilojoules, then that would be valid for this equation here. This is always valid because this doesn't care how many moles. It could be 1 mole, it could be 2 moles, 2 moles double it, 3 moles triple it, 4 moles quadruple it, you know. And so when we don't write them per mole here, then it's written for this reaction as written. And this reaction as written has 2 moles of water. So this 572 kilojoules would be for 2 moles of water, not 1 mole. Let's see what the book did. So the book cut it in half, do you see? So 286, you can add that there. It also cut this in half. So this delta H, you see they didn't write it kilojoules per mole. This delta H is for the reaction as written. The reaction as written is for 1 mole of water, 1 mole of hydrogen, half a mole of O2. The reaction in an oxyacetylene torch is, well, oxygen and acetylene. Oxygen is the oxidizer, acetylene is the fuel, is highly exothermic, releasing 1.31 times 10 to the third kilojoules of heat to the environment for every mole of acetylene burned. The end products are gaseous carbon dioxide and water. And so here, this is combustion. Combustion, you know, of hydrocarbon forms CO2 and water. So we can just figure out the equation here. C2H2, that's acetylene, that's a gas, plus O2 is going to yield CO2 and water. And so we have 2 carbons here. That means we need 2 CO2s. We have 2 hydrogen here, so 1 water is okay. Then we have how many oxygens? So we have 2 times 2 is 4, plus 1 is 5. And so the easiest way is, well, is this. I'm going to do 5 halves. Because 5 halves times 2 gives me 5 oxygens, and that's what I need. 5 oxygens on the left, I have 5 oxygens on the right. And so I can leave it like this. This is for every mole. So this is per mole of acetylene. And so this is right. And so we'd end up forming 1.31 times 10 to the third kilojoules, or we rewrite this and write it delta H on the side, H2O liquid. That's a standard way. So the standard way it's written is the bottom one here. And so this is the number of kilojoules for the reaction as written here. This is the Chem 4 way here. They write it as a product. Now, delta H here is minus, you know, the product isn't negative heat. The product is positive heat. This negative just means it's on the right side rather than the left side. I mean, it's being released, that's it. All right, this is energy stoichiometry problems. So let's take a look at these. Quicklime, the common name for calcium oxide, is made by heating limestone, calcium carbonate. So this is what the Romans did, you know, and for concrete. I think I talked about this. This is highly endothermic, so they needed high temperature kilns. So this is kind of Roman kilns. I think I saw a PBS special. It was really interesting. Roman kilns. Yeah. Where they could bake the calcium carbonate. There's lots of calcium carbonate around. Roman kilns. They use the calcium oxide to make these brilliant concrete structures, like the aqueducts, etc. They say Roman concrete, some of the best concrete, you know, and so Roman concrete. Oops, that's not asphalt concrete. You know, build some magnificent structure. Roman concrete is so much better than what? Why 2,000-year-old Roman concrete is so much better than what we produce today. That's interesting, isn't it? So now scientists have uncovered the incredible chemistry behind this phenomenon, getting closer to unlocking its long-lost recipe. You know, what exactly, you know, did they mix together to make Roman concrete? As it turns out, not only is Roman concrete more durable than what we can make today, but it actually gets stronger over time. Researchers led by geologist Marie Jackson from the University of Utah have been chipping away. I'm kind of interested in concrete too, because when I was working at UCSB, you know, there's a Navy base in Oxnard, Point Magoo. And one of the scientists there was looking at, concrete. He wanted to make a better concrete, to withstand the intense weathering and erosion that happens in marine environments. And so I got a glimpse into, what he was trying to do to try to figure out, how to make better concrete. But anyway, it was a pretty interesting project. And then I saw this thing, I was watching TV and I saw this thing about the Romans and Roman concrete. It's pretty interesting. But anyway, go back to our chemistry here. So calcium oxide, this is very, this is what the slowly rotating kilns, which are a type of oven. The reaction is calcium carbonate. What quantity of energy in kilojoules? So if we want to decompose limestone is very common. They also needed coal. So the Romans were lucky to have sources of coal to get that much energy. It's a highly endothermic process. And so they had plentiful limestone and they had coal. And they had time to do this kind of stuff. I mean, who would ever think about baking limestone, What quantity of energy in kilojoules is required to decompose 5.8? So here, this is the same thing. We go from kilograms of calcium carbonate to grams of calcium carbonate to moles, and then here's the mole ratio to energy ratio right here. And so 78 kilojoules for every mole of calcium carbonate. So kilograms to grams, I would have done that. And then grams to moles, and then moles to energy, 178 kilojoules. That's how much energy. The quicklime produced in question 63 is frequently converted to calcium hydroxide, sometimes called slaked lime, by an exothermic reaction with water. So if we take the calcium oxide, this is the reaction I do. This is Lewis acid-base reaction. This is exothermic, so this is releasing energy. What mass in grams of quicklime was processed in a reaction that transferred 291 kilojoules of energy? So what we do here is we go this. This is a little different here. Quicklime, what mass in grams of quicklime? This is slaked lime. So we go kilojoules to moles. This is just one step because for every mole of quicklime, we get 65.3 kilojoules. So this is a one-step conversion. Oh, it's more than one step because I got to go moles to grams. I forgot that. And so kilojoules to moles, moles to grams, 250 grams. What mass in grams of octane, a component of gasoline, would you have to burn in your car to transfer 9.48 times 10 to the 5th kilojoules of energy? Okay, now they've given us a delta HR. And so this negative sign, you got to watch out. The negative sign just means energy is released or produced. And so I get rid of the negative sign when I do the stoichiometry. And so this is the kilojoules for the reaction as written. The reaction as written is 2 moles of octane. And so we're looking for grams of octane. And so what I do is I do it like this because I don't want a negative grams. So I have to change it. Otherwise I get negative grams. If somebody said, go weigh, I'm on a diet, go weigh out negative 10 grams of sugar for me. You'd be, what the heck, 10 grams, negative 10 grams of sugar? What does that mean? Well, the same thing with this, So this is 9.48 times 10 to the 5th kilojoules. That's how much energy is transferred. And so when I do this conversion factor here, I'm going to do, okay, this is per 2 moles. And so it's 2 moles of octane. I'm just going to write OCT for octane rather than write it all out. And that's positive 1.09 times 10 to the 4th kilojoules produced. And so rather than negative here, I'm writing the word produced to show that it goes on the right side of the equation here. Otherwise, I'm going to get negative moles. If I get negative moles, I'm going to get negative grams because I need the molar mass here. And so I don't want negative grams. And negative grams makes absolutely no sense. So this is why I drop the negative sign. But you have to be careful because in thermodynamics, sometimes you carry the negative sign in the calculation. Sometimes you'll drop the negative sign in the calculation. So you can see here, they end up dropping the negative sign because we don't want, you know, we could get negative grams here. It just means you're using up that many grams of octane. Okay. But physically, it makes no sense because they're asking how many grams you have to weigh out. Oh, some definitions. Let's skip these. Here's something. Let's look at this one. Emergency oxygen masks contain potassium superoxide. And the potassium superoxide, you can buy this stuff. It contains superoxide. If you recall, superoxide is O2 with a minus charge. Okay, Moniza, I had a power outage. It's 4 hours. Yeah, fortunately today I did not forget to record. And so today's lectures are all recorded. So don't worry about it. Okay, great. That was the other day that I screwed up. And so this is potassium superoxide here, KO2. It's kind of weird stuff, but it's reactive. Superoxide is reactive. It's an oxidizer because oxygen wants to be -2, and each oxygen here is -1/2. You know, the average. The average is -1/2. -1/2 times 2 gives us -1, and so it wants more electrons. More electrons, better. Emergency oxygen masks contain potassium superoxide. When exhaled CO2, so CO2 reacts with potassium superoxide. So CO2 reacts with potassium superoxide to make potassium carbonate and oxygen. This is a redox reaction here. So the superoxide is an oxidizer. And CO2, when we think of CO2, I normally think of oxidizer, you know? I think of oxidizer because of carbon. And when I think about this, I think of CO2 as an oxidizer because it's not a very good oxidizer, but it can burn magnesium. And so CO2 is normal. But then the oxygen, I think, is being happy as is. This oxygen is happy as is. But peroxide is an oxygen that's very unhappy. And so if this unhappy oxygen sees this happy oxygen, maybe we could get some redox. So normally I think of CO2 as an oxidizer, but in this case, CO2 is a reducer because this one's going to be a more powerful oxidizer that's going to come on and then try to take the electrons from the oxygen. And it's going to do it successfully because superoxide is a pretty good oxidizer. You know, way better than, let's say, oxygen gas. Oxygen gas can't take the electrons off CO2, even though oxygen gas is 0, right? And it wants electrons, but oxygen and CO2 are going to be stable together, you know? And so oxygen is not strong enough to strip off these electrons on this one, but superoxide is. And so how things behave depends on what you mix it with, you know, CO2. And so here, superoxide oxidizes the carbon dioxide, the oxygen in the carbon dioxide, and makes O2 gas. And so as you exhale, you're exhaling CO2. That CO2 comes in contact with the potassium superoxide, and the potassium superoxide generates oxygen. The oxygen produced can then be inhaled, so no air from outside the mask is needed. So this is self-contained. This is solid. You don't have to have a huge tank. And the gas, this is what you're exhaling. And so you have a small tank of KO2 solid. If this were a gas, then you'd need a large tank for this. If the mass contains 125 grams of KO2, you know, most solids are about twice as dense as water, 2-3 times as dense as water, most solids. So 125 grams of KO2, how many grams of oxygen? So this is just stoichiometry, standard stoichiometry. So this is one of these masks here. That's actually kind of big, so there's probably a lot of KO2 in there. It better be a lot lighter than carrying around a heavy metal tank. And so grams to moles, moles to moles, moles to grams, 42.2 grams of oxygen for every 125 grams of KO2. Yeah, cakes and pastries need CO2 to make the batter rise. Citric acid can be used to react with baking soda. So here's citric acid. Citric acid is soluble, you know. Lemons have extremely high citric acid content, you know. I think it's 80% lemon. Kidney stones, which yeah, I think it's 80%. It's not coming out right away, so I don't want to look for it. Huge. So another, this is a limiting reagent here. We're given the amount of one reagent, we're given the amount of another reagent. So whenever we're given two amounts, it's automatically a limiting reagent. And how much unreacted do we have? Citric, this is interesting nomenclature here. Ic acid means the anion name. If we have ic acid, the anion name is citrate. It's got to be 8. And so this has got to be called sodium citrate. Ic acid is 8. So citrate ion, sodium citrate is what we have. Okay, this is a type of problem I talked about in percentages here. This was a good one here because this is different now. We got a lot of the same kind of problem, now something different finally. A laboratory test of 12.8 grams of aluminum ore yields 1.68 grams of aluminum. If the aluminum compound in the ore is aluminum oxide and it is converted to the pure metal by reaction, okay, here aluminum oxide is the oxidizer, carbon's the reducer. We're going to form aluminum metal and CO2. What is the percentage of aluminum oxide in the ore? And so what we have is we wanted the percent Al2O3. And so this is kind of a combination of algebra and stoichiometry. So we want percent Al2O3 by mass. This is mass percent. And so this means I need to figure out how many grams of Al2O3 per grams of ore. The grams of ore is given here. I have 12.8 grams of ore. And so that's given 12.8 grams of ore times 100%. Problem is I have to find out how many grams of Al2O3 there are. And this is the stoichiometry part here. So this is a mix of algebra because the algebraic equation for percentage, parts per 100. Well, this is parts per 12.8 parts. To normalize it to 100, we multiply by 100%. Now the stoichiometry part, we just use our standard stoichiometry. What are we given here? We're given 1.68 grams of aluminum. So if we have 1.68 grams of aluminum, we could figure out how many grams of aluminum oxide we had. So we'll go grams of aluminum to moles of aluminum. So grams of aluminum to moles of aluminum. And then moles of aluminum to moles of aluminum oxide, or alumina. This is called alumina. So it's going to go to moles of aluminum oxide, Al2O3. And then moles of aluminum oxide to grams of aluminum oxide. And this is going to give me the grams of aluminum oxide that was contained in the ore that was processed here, divided by the grams of ore, 12.8 grams, times 100%. Okay. Okay, so it's a combination of algebra and stoichiometry here. Let's see how the book did it. So the book did the stoichiometry first here, 3.17. I did this, the percent, you know, we're given the grams of ore, the total mass. So we need to figure out what's on top. So I combine it into one. That's fine, 24.8% aluminum oxide in the ore. 76, how much energy is required to decompose 1.42 grams of KClO3? So this is just standard, you know, energy stoichiometry. Grams of KClO3 to moles of KClO3, moles of KClO3 to kilojoules. Now this number of kilojoules is for 2 moles of KClO3, so we got to make sure we got the ratio right. This number of kilojoules are for 2 moles, so we do the gram to mole and the mole to energy, but keep in mind it's the way it's written here. It's not kilojoules per mole, it's kilojoules for the reaction as written. Okay, 77 is the phosphate, did that already. A sludge containing silver chloride is a waste product from making mirrors. The silver may be recovered by, okay, so we don't want to waste the silver. And so this is the waste product. We can recover the silver by dissolving the silver chloride in sodium cyanide solution and then reducing the silver with zinc. The overall reaction, I don't, what I like to do is I like to break it up. You know, when we dissolve the silver chloride in sodium cyanide, that's what we call Lewis acid base reaction. And so I'd like to break it up into steps. Now the first step is silver chloride is insoluble in water, not soluble, so it's a solid. But we could get it to dissolve by adding 2 sodium cyanides for every silver. And this forms this thing called dicyanido silver ion. Cyanide is great at attacking metals like silver and gold. Cyanide they use to extract gold out of old mine tailings. And so of course, it's very poisonous too. And so this is Lewis acid base plus, etc. And so this gives us a way to dissolve silver chloride or silver ions in solution, but it complexes this. This is in Chem 1B. Unfortunately, we don't have time to do this in Chem 1A or Chem 4 or Chem 1A. And we get this. And then the next step is to reduce the silver. So we're going to add, in other words, well, silver ions are a good oxidizer. So we're going to add zinc metal. Zinc metal is a good reducer. And so when we add zinc metal to this, you know, silver ions love zinc. We take 2 silver ions, and it's going to make silver metal, 2 silvers plus Zn2 plus. And so even with these complexes like this, you know, with the 2 cyanides on there, the silver ions are going to be oxidizing the zinc and precipitating out silver metal. And we end up, the zincs end up being complex with the cyanides now. And so this is actually a complex anion here. And so even though this reaction looks very complicated, we can break it down into simpler steps and then add all those simpler steps, and we get this complex reaction here, which isn't really so complex. It's just a combination Lewis acid base reaction and redox. That's it. Well, anyway, that's Chem 1B type stuff. So let's take a look at what they did. So what minimum amount of sodium cyanide is needed to dissolve all the silver sludge from 40 kilograms of sludge? Okay, that's easy. That's stoichiometry. But this is the hard part. This is the little loop that they were in here. That is 23.1% by mass silver chloride. So what they're giving us is, they aren't giving us kilograms of silver chloride. They're giving us kilograms of sludge. All right. So what we have to do here is, that's sludge is a mixture. And so we go from 40.1 kilograms of sludge. And like I said, I do it always the same. So I could leave it as kilogram percentage, but I'm not. And so I'm going to go from kilograms of sludge to grams of sludge. And then I'm going to use this 23.1% by mass. So that means we have 23.1 grams of pure silver chloride per 100 grams of sludge. And then I'll go moles of silver chloride to moles of sodium cyanide, and moles of sodium cyanide to grams of sodium cyanide, and grams of sodium cyanide to kilograms of sodium cyanide. So just turn into straight stoichiometry. So kilograms of sludge, they used rather than gram percentage, kilogram percentage, which is fine. I mean, this is not too complicated, I suppose. But I don't like this kilomole business. But it's okay. And I don't like kilomole ratios either. Or molar masses. But, you know, to each their own. So this is a little bit complicated because of the percentage there. Here's another percentage problem. Is this a mixture or what? Hydrogen and chlorine are produced simultaneously in commercial quantities by electrolysis of salt water. So when we electrolyze salt water, pass electricity through it, we can form some sodium hydroxide, hydrogen gas, and chlorine gas. We looked at this on the first part of chapter 10. Yield from the process is 61% by mass. Oh, okay, this is a percent yield. So for every 100 grams that we think we're going to get, the theoretical yield, we only get 61 grams. That's the average yield. So what mass of solution that is 9.6%? Oh, now they're throwing multiple percentages. They're throwing multiple percentages and see if you get confused. Lots of people will get confused here. And so we got to keep track of them by, you know, what a lot of people do is they don't keep track of things. And so a lot of people just say, okay, 61%, that's 61 out of 100. No units there. And then they'll 9.6%, that's 9.6 out of 100. And then they'll throw them into the stoichiometry and hope it works. Hope they got it right side up rather than upside down. And so, of course, we're going to have to label it. So the yield from the process. Okay, the yield of what? What are we looking for? And so what mass of solution must be processed? Chlorine. We're looking for chlorine. And so this means we get 67 grams of chlorine actual yield for every 100 grams of chlorine theoretical yield. I'll keep track of that. And then what is this 9.6%? Okay, by mass of sodium chloride. Well, that's original salt water. And so this is 9.6 grams of pure sodium chloride per 100 grams of salt water. And so they're asking what mass of salt water, what mass of solution. And so we're after the mass of solution to process 105 kilograms of chlorine. So I would go 105 kilograms of chlorine. This is pure chlorine. We want to obtain this. And so this has got to be the actual yield, not the theoretical yield, but the actual amount we get, 105 kilograms of actual yield. And then, oh, here it's actual yield here. We have to flip this upside down, but I'm going to go to grams. And so I'll go kilograms to grams, 1,000 grams. per kilogram. And then I'm going to go actual yield. Here's grams of chlorine actual yield. And so 61 grams of chlorine actual yield. You better be prepared to make 100 grams of chlorine theoretical yield. Okay, so we need to flip this one upside down. Okay, then once we get grams of chlorine theoretical yield, then we're going to go to, I'm not going to do the whole thing. We're going to go to moles of chlorine. And then from moles of chlorine, we'll go to moles of sodium chloride. And then from moles of sodium chloride, we'll go to grams of pure sodium chloride. And from grams of pure sodium chloride, we'll go into grams of salt water or solution. I'll just call it salt water. Okay, going in this one, we have to flip this one upside down as well. The conversion factor for this is for every 100 grams of salt water that we need, we'll have 9.6 grams of sodium chloride here. And then we'll go to kilograms. So this is a challenge because there are two different percentages there, but it's not hard as long as you label everything, because there's only one way to fit the puzzle pieces together. You know, if you have a puzzle, each piece has a distinct, shape. But if you just say, oh, they're all the same shape, they're all circles, you cut them all into circles or cut them all into squares, then, they don't. So if you eliminate all these units here, then you're losing sight of the shape of that thing. And so we ended up flipping both these percentages upside down. That's the only way to work. Sometimes we have them both right side up. Sometimes we flip only one upside down and the other right side up, It just depends on the problem. All right, okay, let's look at the next problem here. Fluorides retard tooth decay by forming hard acid-resistant calcium fluoride layer. So they react with calcium in the teeth, and this is a precipitate, calcium fluoride. If at the time of treatment there are 239 milligrams of calcium hydroxide on the teeth, and the dentist uses a mixture that contains 305 milligrams of stannous fluoride or tin fluoride, tin 2 fluoride, has enough of the mixture been used to convert all the calcium hydroxide. So in other words, we want the calcium hydroxide, your teeth, to be the limiting reagent, and we want to have excess tin 2 fluoride, And so this is an interesting problem here because we got to figure out which one's the limiting reagent. Okay, if we didn't have enough fluoride to react with your teeth, how much more fluoride do we need? So this is different than all the other problems. We're going to calculate not how much excess remains, we're going to have to calculate, how much, well, there are different ways of doing it. We could calculate how much excess remains and then figure out how much fluoride, additional fluoride we need for that. Or we can, actually there are a number of ways we could do it. So let's see, they're doing comparison, 505. So they just look, your teeth require 505 milligrams of tin 2 fluoride. But you only had 305 milligrams. And so we need another 200 milligrams, basically. And there are other ways of doing this. Oh, yeah. In 1866, a young chemistry student conceived the electrolytic method for obtaining aluminum from its oxide. This method is still used for the reaction. A large amount of electrical energy required limits the process to areas of relatively inexpensive power. How many kilowatt hours are needed? And this electrolytic, there's another way that that they did this. This is a very slow reaction to make aluminum. Used to be very expensive because it was hard to refine the ore to get the metal. And this was another TV documentary I watched. Another TV documentary I watched is somebody figured out a way to dissolve aluminum oxide. Aluminum oxide is extremely tough ceramic. Aluminum oxide is the wonder material, you know, it's the wonder ceramic of ceramics. I used to use it all the time. I used to buy aluminum oxide pots, aluminum oxide labware. It's called Alumina labware. It's amazing stuff. You know, I went to a talk where they had single crystals of aluminum oxide are transparent, you know, totally clear, colorless. And they had aluminum oxide goggles. And they could dope them with certain materials, make them go opaque with an electric current. Let's see. So this is the type of stuff I bought. Extremely high melting point. Extremely unreactive. All this stuff. This is really tough too, you know. Well, it can chip and stuff, but it's really tough. It's not like porcelain. You know, this stuff is way better, way better than porcelain. But it also makes it extremely unreactive. I mean, how do you, this is what ore is made out of, you know, the aluminum in nature consists of aluminum oxide. Like this is like sand, you know, how do you get the aluminum? How do you extract the aluminum from alumina? Not so easy to do. I had all this stuff. I was working with it. Yeah. So, so the guy who developed a way to dissolve this stuff doesn't dissolve in water. This stuff doesn't dissolve in acid. This stuff doesn't dissolve in base, you know. This stuff just doesn't dissolve. And he figured out a way to dissolve it. And the guy who figured out a way to get it to dissolve and then electrolyze it to get aluminum metal, all of a sudden the cost for producing aluminum dropped, you know, dropped through the floor basically. And aluminum became very cheap afterwards. Aluminum became very cheap, and that guy who developed it became very rich. So the guy who developed it became the richest person in the world at the time. Equivalent to, you know, even I guess he amassed more wealth than like Jeff Bezos, you know, in his age. So there's a documentary about that guy. It's pretty interesting about this process, and it's so simple. You think, why didn't I think of that? It's so simple. But anyway, that happened around the turn of the century. It's still, you know, I guess, relatively expensive. So anyway, this is just a gram to mole to energy. Now there's just one more step here. We needed one more conversion factor, and that is the kilojoules to kilowatt hours. So they're 3.60 times 10 to the third kilojoules per kilowatt hour. This is given. So it's just one more conversion using one more conversion factor, which is given here. That's it. And so we just tack on one additional conversion factor to our standard. No problem there. Nitroglycerin here. Okay, the student was given 1.6240 gram sample of a mixture of sodium nitrate and sodium chloride and was asked to find the percentage of each compound in the mixture. So this is not pure. This is a mixture, right? Come on. This is a mixture. And so this is the total mass. She dissolved the sample and added a solution that contained an excess of silver nitrate. Now, silver nitrate will not react with sodium nitrate, but silver nitrate will react with sodium chloride because silver ions love chloride ions. The silver ion precipitated all the chloride ion in the mixture as silver chloride. It was filtered, dried, and weighed. Its mass was 2.056 grams. What was the percentage of each compound in the mixture? So this is what I do for these types of problems. I do like a hybrid of algebra and stoichiometry. And so what I'll do is I'll figure out the percent sodium chloride, because that's, you know, what the silver nitrate react with. Silver nitrate reacts with the sodium chloride, but not the sodium nitrate. You know, silver nitrate plus sodium nitrate will just yield sodium nitrate plus silver nitrate, no change. And so the percent sodium chloride is equal to the mass of sodium chloride over the total mass. The total mass would just be the mass of the mixture times 100%. And so the total mass is given. The total mass is 1.6240 grams, 1.6240 grams total. Now the mass of sodium chloride, we get that from stoichiometry. And so this is stoichiometry, this is given. And so, so we want grams of sodium chloride. What do we have? We have grams of silver chloride. And so we got 2.056 grams of silver chloride. And we go to moles of silver chloride. And then from moles of silver chloride, we'll go to moles of sodium chloride. And from moles of sodium chloride, we'll go to grams of sodium chloride. And so that will give us grams of sodium chloride in the mixture on the top, and then total grams on the bottom times 100%. And that's going to give us a percent sodium chloride. Now the percent sodium nitrate it's a two-component mixture. And so it'd be, the percent sodium nitrate is just 100% minus the percent sodium chloride. So percent sodium nitrate plus the percent sodium chloride has to add up to 100%. So 100% minus the percent sodium chloride is going to give us the percent sodium nitrate. So let's see what they did here. So we have the equation here. So they calculated the grams of sodium chloride here. And the grams of sodium chloride over the total grams times 100% gives us the percent sodium chloride. They did it differently. They figured, okay, if this is the grams of sodium chloride, then the grams of sodium chloride plus the grams of sodium nitrate have to add up to the total. And so they calculated grams of sodium nitrate, which is the difference here, and then did the percentage this way. I would have calculated the percentage here and then just did 100% minus that. It would have been quicker for me here. But either way, it doesn't matter. A researcher dissolved 1.382 grams of impure copper and nitric acid to produce a solution of copper 2 nitrate. The solution, is it time? Okay, it's, yeah, sorry, it's break time. I missed that. You can come off mute and give me a verbal anytime if I miss it. Sometimes I don't look at the chat. Okay, so let's take a break right now. I'll see you guys back in 15 minutes or so. Okay. So let me stop the recording here.